All right, well, thanks very much. It's great to be back at Condor Week. It's been a couple of years since I presented here. And right off the bat, I just want to point out my collaborators, Sam Congdon and Brendan Wakefield, are both cloud engineers at the U.S. Geological Survey, where I work. And they enabled and designed all of the sort of the cloud technology that I'm going to be talking about today. And then Jay Laura is a geographer at the USGS Astrogeology Science Center. Yes, we also cover other planets. And so his project was the Mars Reconnaissance Orbiter data that was the other subject of this talk. So just a quick overview on the Condor technical side. I want to talk about sort of building on the legacy of Condor Annex. We've created a sort of cluster on demand or pool on demand platform in AWS through the US Geological Survey to enable high throughput computing with Condor. And I'll talk about motivations a little bit and how we architected that. And then I want to make an illustration of using high resolution imagery data from the Mars Reconnaissance Orbiter camera. That was the camera on the first slide. So it's an orbiter that's still at Mars and takes very high resolution. By that I mean pixels like this big, images of Mars, of the surface of Mars. All right, so jumping right in. So we've been running a large cluster around 3,000 cores here in Madison for many years. And we've had millions of hours of throughput using Condor, and it's been super successful. So why would we think about moving beyond that and to the cloud? And part of it, I will say, is not listed here, is there's just some institutional motivation. We're having a really hard time buying and maintaining hardware for reasons that I do not understand, that are because of the agency I work for. But it's also true. It can be difficult to buy and maintain on-premises resources. And you really got to think, I used to think, well, I would make these charts of our throughput and start looking at cloud throughput hours and kind of think, we're still doing better on premises. But, it's hard to bring in every single cost. Certainly power and cooling, like exactly how much is that costing our center? The human cost of maintenance, our machines break all the time. It's probably just us, but there's a lot of maintenance there. There's a lot of software and networking maintenance, the equipment in the first place. And even, if we've got this thing that runs in spurts, we're always cooling that room and we always have those machines powered up. There have been some cool talks in the past here about shutting down machines that are idle. And we've loved that idea, but never had the time to deal with it. So whereas if you're cooking a thing, okay, it's out in the desert, but you're cooking a big cluster on cloud all the time, there's maybe a lower carbon footprint overall. All these costs matter. And then who gets priority? So there's preemption and priority things. We've also never been able to implement that on our cluster. So there's been a lot of sharp elbows to make sure that people get their work done. So what about cloud? And we looked at cloud like a decade ago, and before we were even using Condor, so maybe a few years before that. And it was pretty good, but there were some institutional barriers that made it difficult for us to just swipe the credit card and start running things. But there's some great things, right? You can scale really big in theory. You can configure it however you want. That's pretty awesome. You're bringing the compute to the data. So even though I got roundly booed by saying I don't care about data moving yesterday, it is important, of course. But I do care. It was a moment of weakness. But like you've got egress or ingress and egress costs to get to cloud. But once you've made those costs, moving the data around can be pretty cheap or free. So bringing the compute to the data is a good thing. And everyone gets their own cluster, right? You get a cluster. It's awesome. This takes care of the priority issue because everybody's just spinning up their own little world. The downside, I mean, the IT nerdery overload, I would say. So I am not a computer scientist. I sometimes pretend to be. I'm trying to make these things work and do the science at the same time. And to me, there's just so much jargon and challenges in like going to a new place. And maybe it's just because I'm dumb, probably, but I think you can't really overlook that. And a lot of the people that I work with, are in the same boat. They're scientists that are just trying to get a bunch of work done. And if they're like, oh, by the way, go invent a way to do this on the cloud, like with institutional challenges as well, it just doesn't happen. And there's this concept that I've discovered in kind of looking at repeatable workflows called the ubiquity of error, right? Software doesn't maybe have errors, it totally has errors. And models totally have errors. So you run things more than once, but the challenge is this thing, right? The meter's running when you're on the cloud. It's a little bit different than when you're on premises and things are seemingly free. Oh, wow. That's cool. Preview. I have no idea how that just happened. That's awesome. So we've got some code we've put it out on GitHub now, and we're calling it Cloud HT2C, the high test project that USGS paid for a lot of this, and then high throughput rights too. So clever. And this is kind of how it's architected basically. You just got to configure an AMI, an Amazon Machine Image. This is working in Amazon for now. And for those, probably a lot of people are familiar, but if you're not, I think of the AMI as like a blueprint, and an instance, a single running instance is like a building you built from that blueprint, right? But you can have, and it's a little bit like using a container or a VM. There's a few prerequisites for that AMI. Internally, we've got some just kind of sitting around that we just inherit. Externally, in the code, we document what those prerequisites are. And then we're using a technology called CloudFormation. And it's a little tricky because CloudFormation is a way to spin up a bunch of machines of similar type. And it's kind of intended for spillover for things like buying stuff or clicking on your phone, like the main cloud uses, right? But, and so one of the issues is that if a machine goes away, it pops right back, right? That's the idea with CloudFormation. So we've had to do a little bit of trickery to make it be a cluster that is all behaving as one group. That's what we need for a cluster to operate, but also to be able to have things time out and go away for certain reasons. So, but it works really well, and there's a YAML configuration that's pretty straightforward to get this thing set up. And you basically say, which AMI do you want? What kind of architecture? Do you want a whole ton of machines that each have 4 cores? Do you want a couple machines that each have 96 cores? Those kind of decisions. How many workers do you want in your pool? And then optionally, you can choose the spot market, which is quite a bit cheaper. And then there are some timeout options. And then CloudFormation kind of coordinates all this. The single central manager can be put into suspended state, so you're not paying for it, and the workers can come and go. But the cool thing is every worker that you light up knows what the address of the central manager is, and they are instantly in communication. So you can have, for example, you could set up your central manager and you are working on it for a little while, getting things kind of dialed in with one worker. And once you're convinced everything's going to work, then you spin up, 100 more workers and keep going. So it's very flexible that way. And there's a few ports that are open by design. Obviously 9618, we all love that port. But then there's a couple more ports because we use another master worker process under the hood a lot. So Uncle Greg told us there are 12 differences between HTC and HPC yesterday, but a big one is data, right? Data, it comes back. I know, whatever. But so in a way, I'm thinking of this work as kind of in some ways a hybrid of HPC and HTC. Obviously, the part of HPC where everything has to be networked really fast at that expense, we're not dealing with. But data management is really different and we have some more options in the way that we've architected this. Our on-premises stuff, we always use the Condor transfer protocols and push our data around. That's just what we've done for many years. And we can still do that on cloud. But the other thing is, it was pretty straightforward to just have a common mounted directory. It's just, /mount/Condor working. So every central manager and every worker that shows up have this shared space, which means we can move stuff super fast. That's cool. The uncool thing is EFS, which is pretty cheap, is also pretty slow. Like if you try to untar a large file there, like it's time to go make a couple pots of coffee and come back later. So And or you know, if you have a whole bunch of models all reading the same files from EFS, that's very slow. So what we're finding is, depending on the task, depending on the job, some combination of moving the data through Condor transfer, sticking it on this shared working directory, or pulling and pushing from S3, some combination there seems to work pretty well. And we use Globus to get from laptop land out to S3, and then we just sit back and watch it all happen. So how do you configure this thing? I said that there's a YAML file, but a great way that, like, internally we're interfacing with that is something called a service product. By the way, I thought there was a lot of jargon in the computer science that I did, and then I went to the cloud, and there's like, it's unbelievable. But a service product, but it's a great thing. This may be hard to read, but I'll just kind of give the highlights. So the first thing you have to do is sort of name your cluster, because then all of the computers, all of the instances will have that name prepended, so it's easy to search for machines. And a little bit of networking stuff that's generally pretty default. And then you decide how do you want to configure your controller, your central manager. And so you basically decide one of the architectures of the many that are available in Amazon, how much memory you're going to need, and what AMI it's inheriting from. Poof, that's done. And then you go here and you say, how many workers do you want? And also what kind of architecture do you want for those workers as well? And how much memory on each? And they can actually have a different AMI as long as it has those prerequisites that were required. And I just want to point this out. This we stole from Condor Annex, which we stole via Todd, who showed us how this was done in Condor Annex. So this is, or as Marone might call this, embarrassment prevention, also cost overrun prevention. But this is a worker node timeout. So if a worker is idle for this amount of time, it will leave the group and you will stop paying, which is pretty key. And then we also have like the dead man switch. So there's a timeout. You can say in 6 hours, I don't care how much science you're doing, it's done. And this is an important part of my workflow as a modeler, because I always submit Friday night at 7 p.m. when I'm really trying to get out the door to go do something else, because everyone's dutifully gotten me their model by 5 o'clock on Friday. Maybe it's just me. And so without this timeout stuff, it flipped the whole thing on its head. It meant starting these things at 6 in the morning and babysitting all day to make sure you weren't letting things run past their due date. So this is a great addition. And then you can configure spot instances as well if you want. I'm going to zip through this, but just kind of there's a continuum then of how we deploy dependencies. Like I mentioned, you can put a lot of information on that shared directory. I often put a Conda environment in that shared directory and just stick it at the front of my path, and that's performance. Maybe reading files in your model is not. And we're Python people for the most part in my group, and we're finding like Conda pack is also, not only can you pack up a whole Conda environment, but you can stick quite a few binaries in there. So just having a Conda packed environment can be an efficient way to move things around. When it comes to Windows things, we tend to use Wine. We can talk about that more later. I don't use it as much as I used to. And then you can configure your AMI, which is really nice. You can put dependencies if you've got a complicated set of libraries for compilers, or you can use Docker. But as Brendan on our team pointed out, AMI is kind of the OG Docker, right? And I mean, in some ways, it's a lot easier to use Docker because you could use it in a different environment, but the AMIs are quite robust. And again, maybe it's just me, but every once in a while I've had some problems with Docker. So that are my problems. All right, cool. So that's how we cloudify this stuff. So what about Mars? Why am I talking about Mars? So the Mars Reconnaissance Orbiter is there for quite a few different missions, actually, and it's part of the sort of Internet of Mars to be able to transfer information back to Earth more like as efficiently as possible, but also has these great cameras. So, but the big issue is the images come back as JPEG 2000, and they're not really registered just like photographs, right? And so there's a couple issues there. You need to project them onto a sphere and make sense of that and register it in coordinates on Mars. And also, they're big and they're very high resolution, as I mentioned. But if they're in JPEG 2000 format, if you go out to get one, you have to download a maybe a gigabyte of imagery just to take a look at it. Whereas cloud optimized geotiffs are cloud optimized. So that means that they have various resolutions so that you can look at them through a browser and bring them down much easier. It's more explorable. And then putting these things into common projections really enhances interoperability for the scientists. But one of the cool things about this is that these data are openly available, but the path from JPEG 2000 to cloud optimized geotiff and the reprojection and stuff requires a lot of Mountain Dew and very few showers. So what ends up happening is a beginning graduate student wanting to get into planetary science spends tons and tons of time trying to make this translation. And so NASA, in collaboration with us and in collaboration with Amazon, who's paying for the hosting of this data, just said, look, why don't we just process the entire data set and make it openly available so that we can make the pipeline from thinking of science to doing science a lot easier for the people that are trying to do the science and not just fussing with this like really complicated workflow. So that's what we wanted to do. And so here's the work that we did. And and originally this was being done on premises on high performance machines, which worked. It was okay. But part of the argument that we've been making is, and Marone has said this before, like, if you think about the percentage of high performance jobs that are actually high throughput, it's what, 90, 95%? I mean, it's a lot, right? And every time we divert a high throughput job off of a high performance resource, that high performance resource can be used for the things that actually need it. There are fewer, but they actually need it, right? So it's kind of everybody winning. But we wanted to also explore doing this in the cloud. So that's how these things came together. And it was 155,000 plus total images. The input was 100 terabytes, and it was in one S3 bucket, and the output went to the registry of open data on S3, and it was a little bit bigger because there's some new metadata. We spun up 2,000 machines of various numbers of cores and had 4,600 concurrent jobs. And the total wall time for this was about 4 hours. I'm not gonna lie, I got it all going, and I didn't know about Condor Watch Q, so I did watch Condor Q. On one laptop and watched The Martian once on the other one because it just seemed appropriate. My wife actually insisted because it was nighttime also. But unfortunately, we couldn't get through the movie twice because it only took 4 hours. And there was a budget, that was put out for this, and we came in at 2% or 10% of that budget. So spot instances for the win. So this is the team, the exciting launch party, 2,000 things going. You can see that they all showed up in Amazon as well. And then this is a lot of dots, right? But I just want to point out that we kind of hello worlded this thing, and we had some behind the scenes trickery that we had to deal with. And then we said Condor submit 155,000 jobs, yawn, lots of dots. And then right after that, we started seeing this, right? They're running. It was flawless. It was really amazing. 24 are held. That's because they ran out of memory, but we knew that was going to happen ahead of time. No big deal. And just really briefly, so this little blue streak you can see there is one of the orbit pathways on a lower resolution image. And we can zoom in a little bit and zoom in a lot more. And you can start to see actual things, right? Instead of just a few gray pixels, you see sand dunes. And that's scientifically important. We'll just zip through the money here really quick. I mean, it's about, the point is that spot pricing is about 40%. That's a good thing. But spot pricing is kind of like dealing with preemption, right? You might get kicked off. So you just got to think about whether that's right for you. Why is this cost 20 cents? Whereas in spot pricing, whereas the other one is 17 cents. That's this thing. We will talk about that. And so basically, we're coming in at about 6 cents per CPU per hour. We reserve a little bit for the operating system. but it can be like 2 or 3 if you use Spot. So it's starting. I mean, people have been saying this for years, but I'm finally convinced that this is competitive. And so if anybody's interested, kick the tires on this thing, but also please feel free to reach out if you do, because we've got kind of 2 parallel tracks. Our internal code base and what we've put out there aren't always fully in sync. So definitely don't hesitate to reach out if you're interested. Thanks very much.